everyone, Sam from Developing Mathematical Thinking, and in this video we're going to work on dividing decimals. And if you watch the decimal multiplication video, you'll notice that the numbers here are part of the same number set that we worked with last time when we were multiplying. So what I've just done now is taken the product we got when we multiplied 36 3/10 by 2/10, and now we're going to undo that using the 7 26/100 divided by 2/10. Now, one thing that's really important with these methods is I'm going to think of this question the whole time I'm working on this. How many 2/10 compose 6 26/100? Or how many 2/10 are in, 7 26/100? So I'm thinking about how many iterations, how many copies of that divisor does it take to build that dividend? If you haven't seen the division problem types video with where we addressed it with whole numbers and fractions, you may want to take a look at that video as well, because it explains in more detail that way of thinking about division, because there are other ways to think about division in the real world. But for just this exercise, we're going to stick with that idea. How many 2/10 compose 7 26/100? Now, I'm going to start building an area model. And if you watched our whole number division video, you know that we talk about kind of sweeping out that area model, building it in place value based portions. So I've just drawn a length here that just says I have 2/10. And then I've got two different partial quotients, and we're going to do these together, and then we'll finish by showing how the ratio table is a really nice tool to solve the same division problem. So the first thing I'm going to look at is in this partial quotients, I'm going to keep the divisor of 2/10. I'm going to keep it as 2/10. I'm not going to change it. And I'm going to keep the dividend of 7 26/100 the same. I'm not changing it. In this partial quotients, I'm going to multiply by powers of 10, which is a procedure that you would use in long division as well. And this is going to help us understand why that procedure works. Okay? So first thing I'm thinking of is how many 2/10 will compose 7? Well, I know that one of them is not very much, so I'm going to think maybe 10. Okay, well, that gets me to 2. What about 20? Okay, that would get me to 4. What about 30? That would get me to 6. And then I always like asking just one extra question. Well, what about 40 times 2/10? That's too many. That goes over the 7. And the way I'm thinking about this is, well, I know that 3 times 2 is 6. So 3 times 2/10 would be 6/10. So then I'm going to actually have to multiply that as a 30, not a 3. So you can still think about these as single digits, but you want to then restate it in the actual place values. So that gives me the 6. Subtract that, and I'm left with 1 26/100. Well, over here, I'm going to ask the same question. How many 2s are in 70? Well, will it go in at least 10 times? Yeah. 20? Yeah. 30? That would be 60. So 2 times 30 would be 60. Then I just always double check. 2 times 40? Nope, that's too much. That's 80. So I know right here, that's 30. And what ends up happening is this part of our quotient is exactly the same because we changed both the divisor and that dividend by the same power of 10. It works the same way if you ask how many 2s are in 8? The answer is 4. Well, then if I double the 2 to 4, double the 8 to 16, how many 4s are 16? The quotient is still 4 because I changed both those numbers in the same way. So their relationship stays consistent. And that's why this particular procedure works. Let's go build that section in our area model. And if you watched the multiplication video, you know that we talked about how difficult it is to draw areas proportionally when you're dealing with decimals because these numbers are so wildly different in terms of their measurement. So the best we can do is just at least make sure that 30 is much larger than the 2/10. And that at least keeps the place value somewhat preserved as best we can. Now I'm going to move to 2/10 into 1 26/100. I'm going to think about 2/10 into 1. Well, I know that that's going to be 5. So that gets me close. But what if I just look at can I use any of these tenths as well? And it turns out that I've got this nice combination of 1 and 2/10. Well, if 5 2/10 gets us to 1, then 6 would deal with that extra 2/10. So I know that I can say, well, 6 times 2 is 12. So 6 times 2/10 is going to be 12/10, or 1 2/10, or 1 20/100. Subtract that, and I end up with 600. Same procedure over here. 2, well, I know it will go into 10 5 times, so into 12 will be 6. 7 won't work, it puts us over. And now we have that same pattern that we saw the last time with the 30, is we end up with the partial quotient of 6 in each case because the relative sizes were changed in the same way. So I'm going to put a section here. And again, it's not exactly the right size, but it's close. And now we've got to figure out how to deal with the 600s. And so I'm keeping it in place value. I'm going to say, well, I know 2 times 3 is 6. 2 times 3/10 is 6/10. 2/10 times 3/10 will be 600s. So I'm going to go through that whole problem string. And we find that our partial quotient leads us to get a final quotient of 36 3/10. Same thing over here. 2 times 3 is 6. So 2 times 3/10 will be 6/10. We're getting the same partial quotients each time. And now I end up with 36 3/10. And I'm going to add that section to my model. Again, not perfect, but close to suggesting the proportion. And that's how the area model and partial quotients in 2 different methods are linked together. Okay, so now we're going to look at how we could solve this same division problem involving decimals with one of my favorite tools, and pretty much everyone at the DMTI. We just love the ratio table for just about any situation that deals with ratio proportion or a multiplicative situation. And for division with decimals, it's my favorite technique. So I just want to show you how we could think within this table to still solve this problem. So I'm basically, again, finding how many 2/10 compose the 7 2600s. So I need to get to 7 2600s. So I want to start making some fairly large jumps. And I just like listing 10. Oftentimes when I'm working with decimals, just to be thinking place value. Well, that gets me to 2. So I'm not very close. So I'm going to now list 20. Well, that gets me to 4. Okay, well, I'm going to have to do something else. Okay, I've got 30. Well, that gets me to 6. 40 would be too much. So I know that 30 is the largest number of 10s. So from these other methods, I know that I've got 1 2600s left over. So I want to try to get to 1 or to 12, because 12/10. So I'm going to think again using the 10 rule. So I know that 2 times 5 would be 10. So 2/10 times 5 is 10/10 or 1. But I've got this 12/10 left over. So I'm going to try to get to something with 12. So I know that 2 times 6 is 12. So that means that 2/10 times 6 would be 12/10 or 1 2/10. So now I'm getting close because that's going to be 7 2/10. So all I have left is the 600s. So again, I'm going to use the 10 rule to get to that. So I'm going to say, well, I know 2 times 3 is 6. 2/10 times 3 is 6/10. So 2/10 times 3/10 would be 600s. And if I take those sections, they're the same parts I found in the area model, and I compose them back together, I get 36 3/10 will give me the 7 2600s that I was looking for, because essentially what I did is answered what multiplied by 2/10 gets me to 7 2600s. And if you looked at the decimal multiplication video, you'll notice that I worked with the table in almost the exact same way I did when it was multiplication. The difference was I didn't know the 7 2600s, but I did have the 36 3/10. So I know this is a lot of information. There's quite a few other videos that connect to these ideas. I would suggest specifically taking a look at the 10 rule and the division with whole numbers.